So continuing with our discussion on quantum mechanics, in this video we take a look at the concept of the wave function. The wave function psi of x t. A moving particle has both energy and momentum and as such is a de Broglie wave as we have discussed in the previous video. It has wavelength and somewhere along this wavelength is the location of the particle. For example, if the wavelength of a de Broglie wave is 1 meter, somewhere in this 1 meter length is the location of the particle. But where exactly is the particle located? Where exactly can the particle be found? This question may be addressed using psi of xt, which may be considered to be the wave function that is describing a de Broglie wave. Waves are defined by the wave function. The same goes for the de Broglie wave. It is described by the wave function. Now, normally, say in mechanical waves, the wave function basically describes how the mechanical wave affects the medium through which it travels. So, for example, y is equal to cosine of xt plus minus omega t. That's a typical equation for a sine wave. Y describes the displacements of the particle with respect to what is referred to as the equilibrium position of the particle. For a de Broglie wave, the wave function basically describes the chance of finding the particle within the wavelength. So, in this part of the wavelength, what are the chances of locating the particle? If you look at another point in the wavelength, what are the chances of finding the particle there? That's basically described by the wave function psi of xt. It is the square of the matter wave, the square of the amplitude, square of the wave function, absolute value of psi squared, gives the probability that the particle will be found at a particular position and time per unit length, what we refer to as the probability density. So square of the absolute value of psi is the probability density. From the probability density, we are able to calculate the probability of finding the particle. P from x to x plus delta t, probability of finding the particle in this interval x to x plus delta t plus delta x is equal to the integral of the probability density times dx. This equation reduces to square of the absolute value of psi or the probability density times delta x if the wave function psi slowly varies over the interval delta x. So if there's not much change in the wave function on the interval delta x, it's as if psi is constant. So we can take it out of the integration. We take out psi out of the integration. We are only integrating delta x, dx rather. Integral of dx is just x. So for final minus initial will give you delta x. If we are to look anywhere along the x-axis, so if we, instead of simply going from x to x plus delta x. Instead, we look anywhere along the x-axis. It stands to reason that the chance of finding the particle is 100%. P is equal to 1. So where exactly is the particle? Two answers exist. When the observer is not looking or the particle is not being otherwise detected, the particle is everywhere. The particle can be anywhere. When the observer is looking at a particular location or particular position, the particle from being everywhere, the particle will jump into that particular position with the probability given by P. This jumping of the particle into that position when we look into that position is a process called state reduction or wave function collapse. This answer is called the Copenhagen interpretation of the wave function. Meaning, this answer, these two answers, for the most part, is what is referred to as the Copenhagen interpretation. Meaning, when you are not looking, the particle is everywhere. But when you look at a particular position, there's a chance that a particle will suddenly appear in that position given by the probability P. The bizarre consequences of the Copenhagen interpretation of quantum mechanics was criticized by Erwin Schrödinger or Schrödinger. Schrödinger criticized the Copenhagen interpretation using his famous cat in the box thought experiment. You have a cat that is basically both dead and alive until you take a look inside the box. As long as you don't take a look, you don't know if the cat is dead or alive. So in essence, it is basically both dead and alive. A peculiarity of the quantum theory is that the functions are usually complex functions, particularly the wave function psi. Psi is a complex function, so if you take the square of the absolute value, that's basically psi star times psi, where psi star is the complex conjugate of psi. So you might want to look into the concept of complex conjugate in your mathematics because you might, depending on the problem, you might end up having to apply complex conjugate on psi. So that's it for now. In the next video, we'll take a look at the uncertainty principle. Thank you for watching.